Welcome to the first lecture in a series on abstract algebra. This lecture is going to introduce groups, and we'll have several more lectures on groups, and then I'll follow up with some other topics in abstract algebra, although in a little bit less detail that I'm going to cover groups. So we'll eventually get to rings, fields, a little bit on vector spaces, and even less on algebras. And I'll give you some references along the way. I do have other video series, one on linear algebra that'll go into a lot more detail than I'll cover here when I eventually get to vector spaces. But as I say, this first lecture is on groups, and we'll have a few more lectures on the topic of groups following this lesson. As the name suggests, abstract algebra is an abstraction, an extension of concepts from elementary algebra. I took a few definitions from the internet, which I'll go over with you here quickly. So this one is from Wolfram Math World. Abstract algebra is a set of advanced topics of algebra that deal with abstract algebraic structures rather than the usual number systems. The most important of these structures are groups, which we'll talk about in this lecture in a few minutes, rings, and fields. Here's another definition. Abstract algebra is the branch of mathematics that deals with the extension of algebraic concepts usually associated with the real number system to other more general systems. So we'll actually start out with some examples of groups that are just special cases of the general concept of groups, and then we'll give you a general definition of groups, and then in subsequent lectures I'll talk about some additional concepts related to groups and some theorems. The following information I got from one of the AI applications, actually the Google AI application, which is, at least at the time of I'm recording this, it's called Gemini. So I'll just read from the quote that I got from Google. Abstract algebra is a branch of mathematics that studies the properties of algebraic structures, groups, rings, and fields. So I've mentioned that a few times. These structures are abstract in the sense that they are not tied to any particular set of numbers or objects. Instead, they are defined by their properties, which can be stated independently of any specific implementation. Abstract algebra is a vast and complex subject, but it is also one of the most important branches of mathematics. It has applications in many other areas of mathematics, as well as physics, chemistry, computer science, and other fields. Let's continue with this on this next slide. So on this slide, and in continuing with the readout I got from Google, they talk about the three different main topics within abstract algebra. First one are groups. A group is a set of elements together with an operation that combines any two elements of the set to produce another element of the set. The operation must satisfy certain properties, and we'll talk about those in more detail, such as associativity, commutativity, and the existence of an identity element, as well as an inverse, though not mentioned in the Google definition here. And then there's rings. A ring is a set of elements together with two operations. They're normally called addition and multiplication that satisfy certain properties. The properties of a ring are similar to those of a group, but with the additional requirement that multiplication is associative and distributive over addition. And we'll talk about rings in another set of lectures that'll follow the lectures on groups. And then there's something called a field. Is a ring in which every non-zero element has an inverse under multiplication. Fields are the most important algebraic structures, and they have many applications in mathematics and other areas. And I'll have several lectures on fields after the lectures on groups and rings. So I'm just kind of giving you the roadmap here. And then the Google output concluded with this sentence here. Abstract algebra is a challenging but rewarding subject. It requires a high level of mathematical maturity and abstract thinking, but it can provide deep insights into the nature of mathematics. So For those not familiar, abstract algebra is typically a 2-semester course, sometimes 1-semester course at the junior or senior level undergraduate for math majors, and sometimes other majors will take that, or at least they'll take an abbreviated version of that class. Okay, so let's get started in talking about groups, which will be the rest of this lesson. In terms of preliminaries, I'm assuming the listener is familiar with the basics of set theory, a little bit of number theory and permutations. If you need to brush up on that, I can give you a reference here to a book by Judson. I'll also put this link into the information of this video, so you can just click on the link and not have to type it in. Then you may want to listen to this, at least the beginning of this video here, from Newman. He talks about some complicated things on finite simple groups, but before he gets to that, he kind of gives a nice introduction to group theory, which will complement what I'm talking about, maybe overlap a little bit, but additional information that you may want to take in before listening to the rest of this lesson. Okay, and I'll also put this in the information to this video, so you don't need to type this link in. You can just click on it. So I'd like to start the discussion on groups with an example of something that is a group, and I'll highlight the different properties of groups as we work through the example. So what we have here at the, let me point to it. What we have here are the set of integers, and of course they're infinite, so I can only list a few of them here. You have the positive whole numbers and negative whole numbers and 0, so those are the integers. And this is in fact a group. And let's go through the different properties that make it a group. If we add two integers, we necessarily get another integer. So I just took an example here, -3 and 7, you get 4, and of course that's an integer. No matter what two you pick, or what, you could pick more than two, but whatever two you pick, you're going to get another integer. In general, a set having this property is said to be closed under addition. That's our group operation. Another property is the order of the addition doesn't matter. So you can take 2 and add -4 to it, or add -4 and 2, and either way you get -2. This is known as a commutative property, and that's not a necessary property. Some groups are not commutative, so we'll talk a little bit about those, but that's a property that some groups have. Then with respect to addition of integers, grouping does not change the result. So you can have 2 plus 5 plus minus 11, or you could add the 2 and the 5 together and then add the -11, and either way you get -4. So that's the associative property, and that's a necessary property you need to have it to be a group. Then the sum of any integer with 0 is the integer itself. So -5 and 0 is -5. So that's known as the identity element. You need to have that to be a group. And then finally, you need to have an inverse. So for any integer, you can take the negative of that and you get 0 when you add the two together. And I can just give an example here. So 2 and -2 are the inverses of each other. 3 and -3 are inverses of each other, and so on. Of course, 0 is its own inverse. You add it to itself and you get 0 again. Okay, so these are the group properties. As I say, the commutative one is optional, or doesn't have to hold to be a group. And just a warning here, there's only one operation, addition. There's no subtraction. You add negative integers, and that's effectively what we normally would call subtraction when we're talking about the integers. Okay, so that's not an operation in and of itself. Subtraction is not. As we'll see in a little bit, many other sets with an associated binary operation follow the properties listed above in the previous slide for integers. In general, we have a binary operation. Let me point to it here. Star, with different symbols are used depending on the context, but there's a binary operation on the set G, and it takes two elements, A and B, and it gives us another element that's also in the set G. That's one of the main properties of a group. It's known as the closure property. So let's take another example here. What about the rational numbers, the fractions under multiplication? Are they a group? So we can look here and see these are the different properties we discussed previously. So closure would work, right? If you multiply a fraction times another fraction, you're going to get a fraction, and that would include whole numbers. So you can multiply 2 times 1/2 and get 1, or 2 times 1/3 and get 2/3. Just as examples. You also have 0, and that's actually the problem number in this set here, but we'll get to that in a second. Associativity works. If we have 3 fractions multiplied together, we can multiply the first 2 times and then multiply times the third, or multiply the second and third first and then times the first one, and that's fine. That'll hold. The identity, now we're talking about multiplication, so the identity is now 1. So multiplying 1 times any fraction gives you the fraction back again. It's also commutative. The order in which we multiply fractions doesn't matter. We get the same result. The problem comes up with inverses. Again, remembering that our identity is 1, if we take a number like 2/3, then the inverse would be 3/2. If we take a whole number like 7, the inverse would be 1/7. When you multiply the two together, you get 1. The problem is with 0. There's no inverse for 0. So it's not a group. The rational numbers are not a group. However, if we remove just one element from the set, 0, then the rational numbers with 0 removed is in fact a group. So now we have 2 examples. One is the additive group of the integers, and the second example is the multiplicative group of the rational numbers with 0 removed. So let's look at the formal definition of a group. We've seen 2 examples, and we kind of know what's expected here. We have first the closure that we talked about on the previous slide. When we take 2 elements from our set G and we apply our binary operation, then it needs to be within our set, so we need closure. Then we have the associative law. So we see here we can, I'm going to use the term multiply, but again it could be various operations. So when we multiply A times B, and then multiply that times C, which should be the same as multiplying B times C, and then multiplying that times A, so that's associative. Then there needs to be a identity element, so A times, or E times A equals A. That's the property of having an identity. Sometimes we'll use 0 in the case of additive groups and 1 in the case of multiplicative groups, and in general we'll just use E. Then there's the inverse. So for a given element A in our set G, there needs to be an inverse, so that when you multiply the inverse times A, you get the identity. Alternately, sometimes we'll see the symbol A minus 1 to represent the inverse. It's also true that if you have this, you also have this here. Even if you don't have a commutative group, this is true. And then the last property, as I mentioned before, is optional. Some sets have this commutativity property, and they're known as either commutative or abelian groups. This is named after a mathematician, Abel, A-B-E-L. And we'll see that the two groups that we've seen so far, the integers and the additive group of the integers and the multiplicative group of the rationals with 0 removed, are both abelian groups. And then this is the symbol that's used. So the set G and then your binary operation. We have a few more examples here. As we saw, the integers represented by Z, the double bar Z, point to it here. Under addition is a commutative group. The set of real numbers, represented by this double bar R, and the rational numbers, represented by Q, are also commutative groups under addition. And as we saw, 0 creates some problems in terms of multiplicative groups. I just wanted to put down some notation here related to that. So if you have the real numbers without 0 in it, you write it this way here. And similarly, you could write the rationals without 0 or the integers without 0 using this notation. Sometimes you'll see a minus sign. That just means this set minus the set containing 0. If we consider the operation of multiplication, we have an issue with 0, as I mentioned. However, if we remove 0, the rational numbers, as we saw in the previous slide, is a multiplicative group, and the same holds for the real numbers. If you remove 0, they're a multiplicative and commutative group, actually, under the operation of multiplication. And in both cases, the identity element would be 1. Then we have one more example that'll come up here and there, so let's take a few minutes to analyze this. It's the integers modulo n, and that just means the integers are put into these different classes based on the remainder when you divide by n. So if we use this symbol here, z, double bar z sub n, and it has these n minus 1 classes. And maybe a particular example would make it a little bit clearer. So let's take n equals 5. In that case, we would have 5 different classes for this, turns out this group. And this first class here are all the integers who are exactly divisible by 5. So this class would have 0, 5, 10, 15, and then same thing on the negative side, minus 5, minus 10, minus 15, and so on. Then this class here, 1 bar, would have all the integers whose remainder is 1 when divided by 5. So that would have 1, 6, 11, and then going in the negative direction, you'd have the same thing. You'd have, going back 5 from 1, you would have minus 4, and then minus 9, and so on. And similarly for 2, 3, and 4. So these would be the 5 classes that make up this group. We add them just as we would add integers, except we have to take the remainder after the addition. So if we added 3 and 4 bar here, we would get 7, and then the remainder would be 2. So this sum here would be 2 bar. And then in terms of inverses, 0 is its own additive inverse. When we add it to itself, we get the identity element, which is 0 bar. And then 1 bar is the inverse of 4, because when you add these two, you get 0 bar. And then 2 is the additive inverse of 3, since when you add these two, you get 0 bar. So let's look at the modular numbers, but in this case with respect to multiplication. We'll kind of work through an example. It's actually not a group under multiplication, and I'll show you why that is in a minute. So for z sub 6, we get these 6 elements, and we multiply in a similar way that we do addition, in the sense that we multiply the two numbers and then we take the remainder. So if we take 2 times 4, we get 8, and the remainder modulo 6 is 2. So 2 times 4 is 2. We can take another example. 3 times 5 is 15. Then the remainder, when you divide by 6, is 3, and so on. So this is not a group, although most of the properties hold, but not every property. It is closed. If you take any two numbers here and multiply them, you get another number in the set. The multiplicative identity is 1. So 1 times any of these numbers gives you the number back itself. Associative and commutative laws hold. The problem is with the inverses. 0, 2, 3, and 4 do not have multiplicative inverses. We can take any one of these and test it. Let's take 3. And no matter what element from this set you multiply times 3, you're not going to get 1. You get 0 times 3 is 0. 1 times 3 is 3. 2 times 3 is 6, which is 0 in this set here. 3 times 3 is 9, which gives you a remainder of 3. 3 times 4 is 12. That's 0 again. And 3 times 5 is 15. And the remainder would be 3 in that case. So there's no number in this set here. 1 multiplied times 3 gives you 1. And you have the same problem with 0, 2, and 4. And so we don't have a multiplicative group. The solution is to remove these 4 from the set, and that just leaves us with 1 and 5. So 1 and 5 modulo 6 is in fact the multiplicative group. It's not very interesting, but it's a multiplicative group. We can look at another example. Let's take Z10. It's a little bit more interesting. And the trick here is to remove numbers that are not relatively prime to the set. You notice for, just going back to this for a second, 0, 2, 3, and 4 are not relatively prime to 6. It's only 1 and 5 that are relatively prime. And relatively prime meaning they have no common factors other than 1. So in the case of 10, the numbers relatively prime are 1, 3, 7, and 9. So if we remove all the other numbers from Z10 and we just leave these 4 here, we do get a multiplicative group. And these each have inverses. The inverse of 1 is itself. The inverse of 9 is also itself. 9 times 9 is 81. And modulo 10, that's 1. And then 3 times 7 is 21. So and again, that would be 1. So they're inverses of each other. If we take consecutive powers of 3, so 3 to the first power is 3. 3 squared is 9. 3 cubed is 27, and that modulo 10 is 7, and then 3 to the fourth is 81, and modulo 10, that's 1. So if you do that, you actually generate all the elements in our group here. So this is something known as a generator, that we'll see this concept later on. I thought I would just introduce it here. So 3 bar is a generator for this group of 4 elements. In terms of notation, to distinguish between the additive group, Z sub n here, which we talked about on the previous slide, we write it this way here, it's a little plus sign. And then the multiplicative group, we put a multiplication sign. And then we also have the understanding that we remove all the numbers that are not relatively prime to n. So as we saw in this example, and also with Z6. So if n is a prime number, then the only thing we need to remove is 0, and we get all the other n minus 1 elements in that case. On this slide and the next few slides, we're going to talk about an important group known as the symmetric group. The symmetric group, defined over any set, is a group whose elements are all the one-to-one functions whose from the given set onto itself, in other words, a bijective mapping, and whose group operation is the composition of functions. So rather than take any general set, we normally just use the set 1 to n. We can always map a set of n elements whether they be people's names or letters or whatever. We can always map n objects to the numbers 1 to n. So we just use this set here. And then the symmetric group is denoted S sub n, and it has n factorial elements. So it's all the permutations of these numbers. So you can put any number from 1 to n in the first position, and then n minus 1 remaining numbers in the second, and n minus 2 numbers, any one of those in the third position, and so on. And you get n factorial possible combinations of the numbers from 1 to n. The important part here is all finite groups can be mapped to a subset of S sub n, the symmetric group with n elements, for some positive integer n. More precisely, this is known as the Cayley's theorem, and it says every finite group G is isomorphic to a subgroup of the symmetric group S sub n, where n is the number of elements in G. So let's check that S sub n is a group. We need to check the properties here. So the operation of function composition is closed. So if you take a permutation of the elements from 1 to n and you do it again, another different permutation, perhaps you're going to get collectively a permutation. So that's closed. Composition of functions in general is associative. So in our case here for permutations, we know that it's associative. The identity element is just mapping the number 1 to the first position, number 2 to the second. In other words, you don't permute the numbers at all. You just put them in their position based on their number. So that's the identity. Then we can just reverse the permutations, any permutation to get the inverse. That's pretty obvious. So if you just had, say, n equals 3, and you map 1 to 3 and 2 to 2 and 3 to 1, you can just reverse that and get the inverse. So that also holds. So the different variations, there's different subgroups within the symmetric group, and we'll talk about some of that in the next few slides. Just to make things more concrete, let's look at some examples. Let's take S sub 5, so that's the permutations on the numbers 1 to 5. And from what we said on the previous slide, the number of those would be 5 factorial, which is 120. So already we have quite a few elements, and even just for the S sub 5. Here's one particular example, and we use this notation sometimes. It just says 1, in the first we map 1 to 3, 2 to 4, 3 to 1, 4 to 5, and 5 to 2. And this is actually 2 cycles. You notice 1 goes to 3 and 3 goes to 1. So this is kind of a loop or a cycle. You can write it this way here. Then 2 goes to 4, 4 goes to 5, and 5 goes back to 2. So that's another cycle. So this is another way of writing a permutation. One is this way here, where you explicitly show where each element is mapped to another element, in this case from 1 to 5. And then you can also always break this down into cycles. In some cases, the cycles are just of length 1. If we mapped, say, 2 to 2, then you would just have 2 in brackets here. But in this case here, we have a cycle of length 2 and a cycle of length 3. So that's what I mentioned here. There's at least 2 different ways. I'm just showing 2 here to write out a permutation. And I won't repeat what I kind of just said here. And let's see here. And then here's another example. This is the identity that we mentioned on the previous slide. So 1 to 1, 2 to 2, and so forth. And so that would just be 5 cycles of length 1. Then the inverse is the reverse of an element. And basically what you do is when you take the permutation of and apply the inverse to it, you want to get back the identity here. So you see here that these 2 permutations are the inverse of each other. where we go from, in this case here, left to right. Sometimes you go right to left, and in fact, I think I've probably done that in some of the examples. So I'll try to point out which one you do first here. So we're going left to right. So 1 gets mapped to 3, and then 3 to 1. And so collectively that just takes you from 1 to 1. Then you have 2 to 4, 4 to 2. So 2 goes to 2, 3 goes to 1, 1 goes to 3, 4 goes to 5, 5 goes to 4. So you get 4 to 4 again collectively between these two. And then 5 to 2, and then 2 to 5. And you get the final element here. So these two permutations are inverses of each other. And that's always true. You can always find an inverse for a permutation. S sub n in general, in our particular example, S sub 5, are not commutative groups. So for the inverses, it's true. You can go left to right or right to left, and you'll get the identity. But for the other elements, you don't necessarily get the same solution. So I just took two permutations from S sub 5. They're not the inverse of each other, and we can go this one first and this one, and then reverse the order, and we get different answers here. So let's just check that. We have 1 to 3, 3 goes to 5, 2 to 4, 4 to 1, 3 to 1, 3 to 1, 1 to 4, 4 to 5, 5 to 2, and then 5 to 2, and 2 to 3. So that's going from left to right. We get this here, and we just reverse the order, and you'll see we don't get the same thing. So 1 goes to 4, 4 goes to 5, so far we're okay. 2 goes to 3, 3 goes to 1, 3 to 5, 5 to 2. Then it breaks down on these last two here. So 4 goes to 1, and 1 goes to 3, and 5 goes to 2, and 2 goes to 4. So you see here, these last three here are different. And in general, that's true. I just took S sub 5, but in general, S sub n is not abelian. It's not commutative. There are subgroups which are, but the entire group itself is not commutative. Every permutation can be broken down into the product of one or more cycles. Let's look at an example. Here we have 11 S11, and we have a particular permutation. The way to find the cycles is you start with 1 and then just follow the mapping through here. So 1 goes to 9, 9 goes to 11, and you record it here in a cycle. 11 goes to 10, 10 goes to 3, 3 goes to 4, and then 4 goes back to 1. So once you go back to where you started from, you have a cycle, and then what you do is you take the next number that's not in the cycle, and you see what cycle that might generate. So the next number would be 2, that's not in this list, and we see 2 goes to 7, 7 to 6, 6 to 5, and then 5 back to 2. So that gives us another cycle. And the only number we haven't hit is 8, and you notice that's just a one member cycle. It just goes back to itself. So this permutation can be written in terms of the product of these cycles. The order doesn't matter, and that's because these are disjoint, so you can do these in any order. So this here is the same as this here. Further, it's always possible to decompose a permutation in the product of two cycles and one cycles. For example, this cycle here, 1 to 3, 3 to 2, 2 to 5, 5 to 4, 4 to 6, and then 6 back to 1, can be written like this. You notice how I've done this. It's 1 to 3, 1 to 2, 1 to 5, 1 to 4, 1 to 6. You may not be convinced that this is the same as this product here, but we can do it here to actually prove it. It's kind of tedious, but let's take a look at that. So we'll first go, we're going from left to right, so we'll first do these two. And we can write this out longhand. You notice most of these are just mapped to themselves. You have 1 to 3 and 3 to 1. Then you do the same thing here, writing that out longhand, just so it's easier to see how the mappings go. So 1 goes to 3, 3 goes to 3, so that you get 1 to 3, 2 to 2, 2 to 1, 3 to 1, 1 to 2. And then these last 3 just get back to themselves. And then, so that's the product of these two. And then you just bring this down here and apply 1, 5. So you take this and then 1, 5 written out longhand. Then you go through the calculations. 1 to 3, 3 to 3, 1 to 2, 2 to 1, 1 to 5, 3 to 2, 2 to 2, and then 4 to 4, 4 to 4, but 5 to 5, and then 5 to 1, then 6 to 6. So you get this. And then you just bring this down here and you write out the 1 to 4 here. I won't torch you with all the calculations, but you get this here. Then you bring this down, put it here, you do 1 to 6, and you do the computations, and then you can just follow through here and see what the cycle is. 1 to 3, 3 to 2, 2 to 5, 5 to 4, 4 to 6, and 6 to 1. And that's what we have here. In general, any cycle can be written as follows. So here we have our cycle, and you can write it this way here. So you have A1, A2, A1, A3, A1, AN. We saw that in terms of an example previously, but you also have this possibility, A1, A2, A2, A3, AN minus 1, AN. And this is assuming left to right order of composition. So we start here and we proceed this way, and same thing for this. Here's another possibility. A1, AN, A2, AN, AN minus 1, all the way up to AN minus 1, AN. So these are 3 ways. There's probably more, but these are 3 ways of writing this cycle here. Again, going from left to right. If you assume right to left, then there's slight changes in the order of these. So for every permutation of a finite set can be expressed as the product of 2 cycles known as transpositions. While several such expressions for a given permutation may exist, either all contain an even number of transpositions or they all contain an odd number. So this is an important fact. So no matter how you break a cycle up, it's either going to have an even or an odd number of transpositions. And there's a proof for this. Theorem 2.40 in a book by Rotman, which I referenced earlier, and I'll put a link to this book in the information to this video. So this allows us to classify permutations as being even or odd, since we know that whenever you decompose the cycles into transpositions, you're going to get either an even or an odd number. So having a few examples here, this cycle here can be written in terms of an odd number of transpositions. And so this would be an odd permutation. Then we have this one here, which we saw earlier, and this would have 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 transpositions. So this is an even permutation. And we don't count the 1 cycles. We just count the number of transpositions. The subset of Sn containing all the even permutations over a set of n elements is known as the alternating group of degree n, and it's denoted by A sub n. We have a theorem here. The number of even permutations in S sub n is equal to the number of odd permutations, and so A sub n has n factorial over 2 elements. I'm not going to prove it here, but I'll give you a reference to a proposition from a book by Judson, which I referenced earlier, and I'll give you the link to this book. I believe both of the books, or all three of the books I mentioned in this lesson, are available through the Internet Archive, so you can actually borrow them for a period of time and look through them electronically, so you don't necessarily need to buy these books that I'm referencing. Okay, so let's proceed and have a further look at this A sub n on the next slide. A sub n is a group, and we can verify that here on this slide. If we multiply two even permutations, we get an even number of transpositions, and so the product is also an even permutation. So we have closure. The associative law is inherited from S sub n, so we have that. And then the identity permutation has zero transpositions, so that's by definition even. So we have that in A sub n. And the last part is sort of the hardest in terms of the inverse. We know that each element of A sub n has an inverse, since A sub n is a subset of S sub n, and S sub n is a group. What we don't know is that if those inverses are also in A sub n. So that's what I'm going to show here. So we decompose an element alpha of A sub n into a product of disjoint cycles and single permutations. That's what I've written here. So these are the sigma sub 1, sub 2, sigma sub k are the cycles, they're disjoint. And then these are the one cycles where you just map the number into itself. So there's no need to invert the single permutations. Really the issue is here with these cycles. So let's first look at a general cycle. Not necessarily from alpha, but just any cycle. Its inverse, B inverse, beta inverse, excuse me, is just this in the order shown here. You can write these out and you'll see that gives you the inverse. And so the upstart of that is that B inverse can be decomposed into the same number of transpositions. Remember, we showed in the last slide how to write a cycle in terms of transpositions. So it really depended on how many elements you had in the cycle. And this beta and its inverse have the same number of elements in their cycle. So the inverse of a cycle has the same parity, in other words, even or odd, as the original permutation. So the inverse of alpha is this here, just writing an inverse of each one of these cycles. And each of the sigma sub I, the inverse of each one of those, has the same parity as the original sigma sub I. So we know that the parity of the inverse of alpha, this thing here, has the same parity, in other words, the same number, even or odd number of transpositions as alpha. So that means that if this was in A sub n having an even number of transpositions, then its inverse also does. And so that proves the last part. So A sub n is a group. You may be wondering about the odd permutations, and that's not a group. It violates two things here. If you take the product of two odd permutations, say they have 3 and 5 transpositions, then you get an even number. That's always true, right? When you add two odds together, you get an even. So it's not closed. And then the other problem you have is with the identity. Since the identity, has 0 transpositions, it's in A sub n, but it's not in the set of odd permutations. So the odd permutations miss being a group on 2 counts. On this slide, I have a set of examples, actually, known as the dihedral groups. there's one group for each regular polygon with n sides, and it's based on the symmetries of the polygon. So let's have a look at the details here. A regular polygon with n sides, sometimes known as an n-gon, has 2 times n different symmetries, n rotational symmetries. We rotate the polygon 360 divided by n degrees, and then n reflections. The set of rotations and reflections make up the dihedral group D sub n. Warning, since the group of symmetries on a regular n-gon is of order 2n, sometimes this is called D2n. So you need to be careful in terms of what book or internet article you're reading, just to make sure what notation they're using here. So I have an example, maybe before I get into the details. I have a couple examples actually. So here we have n equals 6, and I think the rotations are fairly obvious. If you just number these 1, 2, 3, 4, 5, and 6, then you rotate it once, and 1 gets mapped to the second position, 2 to 3, and so forth. And then you could do another rotation until you eventually come back to where you started. So those are the rotations, and you would have, in the case of n equals 6, you would have the rotation of 0 degrees, where you just leave it as it is, and then you have 5 more, 1, 2, 3, 4, 5, and until you get back to the original position. So those are the 6 rotations, and then you have 2 different types of reflections, and I kind of showed them with different colors. You have one type of rotation that goes between opposite vertices. So I'm showing one here, and you could flip this across this red line here. So this would get mapped to here, this would get mapped to here, and then these two would remain the same. And then you could do that between these two here and between these 2 vertices here. So you would have 6 divided by 2, or 3 of these rotations, where the axis of rotation is the line connecting 2 opposite vertices. Then you can also connect opposite midpoints, as I'm showing with the green. And then you flip it across this here, and so this vertex gets mapped to here, this to here, and this vertex to here. And then of course you'd have another axis here and another one here. So it gives you 3 more. So that gives you a total of 12 rotations and reflections. And then I have, so that's for when you have even number of vertices. Then if you have an odd number of vertices, it's actually a little bit simpler. You have the rotations, just as I explained before, and then you have, in this case, n is 5, you have 5 reflections, and each reflection is based on connecting a vertex to an opposite midpoint. So you have one here, and if you flip this across this line, this vertex remains unchanged, but this gets mapped to here, this gets mapped to here. And then you can do it between this vertex and this midpoint, this vertex and this midpoint, and so on. So you'd have 5 reflections and 5 rotations. And then what I have here in the remainder of the slide is just explaining this more generally. So if n is odd, like we had in this example here, each axis of symmetry with respect to reflection connects the midpoint of one side to an opposite vertex, as we saw here. If n is even, there are n over 2 axes of symmetry with respect to reflection connecting midpoints of opposite sides. So that's the green ones here. And then n over 2 axes of symmetry connecting opposite vertices, and that would be the red ones here. So in either case, there are n axes of symmetry with respect to reflection. The dihedral group D3 consists of the following operations on an equilateral triangle. We have 3 rotations. 0 degrees, which is the identity, we'll call that E. Then 120 degrees clockwise rotation, we'll call that A. Then if you apply A twice, you get 240 degrees clockwise rotation, and that's A squared. Then there's 3 reflections about the axis between a vertex and midpoint of the opposite side. If we let B be one of the 180 degrees reflections, then the other 2 are just gotten by doing the rotation and a reflection. So it would be A times B, and then 2 rotations, and then the reflection. So between B, AB, and A squared B, we get the 3 reflections. So we have a group of 6 elements. These are the elements here. The various combinations of multiplying the elements are shown in the table, in 2 slides actually from here. It's known as a Cayley table. The elements of the group are listed in the top row and left column. We'll see that in a minute. And it works just like a multiplication table for numbers. We also use some identities here. Some of them are obvious, some are not. So A cubed is just rotating 3 times 120 degrees. So that gives us back to the identity. Then if you do one more, that's the same as just doing A. So A to the 4th is A, and of course A to the 5th is A squared. And then if you do a reflection twice, you come back to where you were, where you started. So that was E. Then these 2 are less obvious. I'll show you this one on the next slide. It's basically just drawing the triangle with numbers on it and showing that if you do this, and if you do this, you come to the same thing. And then you also have that AB does not equal BA. So this is not a commutative or abelian group. Okay, so let's look at this one on the next slide in some detail. And then on the slide following that, I'll show you this Cayley table. On this slide, I want to show that BA is the same as A squared B. So this is our starting point. And we first do B. And so 1 remains the same. And we're using this axis here. So 1 remains the same, but then 3 and 2 get swapped. So we come to this. That's just applying B. And then we do 1 rotation. So 1 goes here, 3 goes here, 2 goes here. So this is the result of BA, going from left to right. Then if we start here and we do A squared first, then this gets 1 gets mapped to this position here, 2 gets mapped up here, and 3 gets mapped here. So this is the result of A squared. And then if we just do B, a reflection about this axis here, then the 3 goes here, and the 1 goes here, and the 2 remains. And you notice these are the same. So BA equals A squared B. All right, so now let's look at the Cayley table. On this slide, we have the Cayley table for D3. This is composition, and the column, the first column and the top row are the elements, and then these are the compositions. So for example, E times any of these gives you back the same element, and if you multiply any of these elements times the identity, you get the same thing again. So this column here and this row here is pretty easy. A times A is A squared. It's just 2 rotations. A cubed brings you back to where you started, so you get the same, you get the identity. Then as we mentioned in the 2 slides back, A to the 4th is A. Some of these other ones we need to use the identities that I mentioned on the previous 2 slides back. I'll leave that as an exercise for you to check. Yeah, and then AB, A times B is this here, and B times A is, as we established, is actually equal to A squared B. So these 2 things are not the same, and as I mentioned, this is not a commutative group. We conclude this lecture with a few more examples concerning matrices. The set of all invertible matrices of size n by n, whose elements from the real numbers form a non-abelian group. We know that matrices are not commutative, so that's why we have this property here. This group is known as the general linear group of degree n over the real numbers and is denoted by GL sub nr. So GL stands for general linear, n is the size of the matrices, and r represents the elements in the matrices. We could also define a general linear group over the rational numbers, and the notation just replaces the r with the symbol q for the rational numbers, or we could do the same with the complex numbers. In general, one can define general linear groups over any field f, so r, c, and q are all fields, so they're just three examples. Such groups are denoted by this notation here. We will discuss fields in a subsequent lecture. Actually, it's not in the set of lectures on groups, but I'll have another set on fields. So as I mentioned, the real numbers, rationals, and complex numbers are examples of infinite fields. We've already seen an example of a finite field, Z, P, the integers mod P, where P is prime. Regardless of the underlying field, all matrices, general linear group, N, F over this field, must have a non-zero determinant, which implies the inverse of the matrix exists. I said that up front here, that they need to be invertible. For those familiar with linear algebra, the term linear in general linear group refers to the rows or columns being linearly independent. The special linear group, represented here SL and F, is a set of matrices with a determinant of 1 over a field F. SLNF, the special linear group of size where the matrices are of size n by n over a field F, is a subgroup of our general linear group. Okay, so that completes our first lesson on groups. I have a few more lessons on groups where we talk about different theorems and a few more examples as we go along. So stay tuned for those additional lectures.